equation 16 is the mass use for thermodynamics. Was derived there. You really need to understand that derivation and be comfortable with that type of argument. We have some new physical parameters that are also talked about in the background of the introduction course. The coefficient of expansion and isobutability, we'll talk about that from time to time. Remainder of the term, the Joule-Thomson coefficient on occasion as well. That is just an experimental property of fluids that is measured by shoving a fluid through a restriction, which is insulated, adiabatic restriction, and measuring the change in temperature for a given change in pressure. So the ratio of the temperature change to pressure change gives the Joule-Thomson coefficient. And that expansion process, that strong expansion process, turns out to be isenthalpic, and that's true in the notes as well. I'll include a rewrite of that here just momentarily. For real fluids, the Joule-Thomson's expansion can be either positive or negative or zero. It has to be zero for an ideal gas, and why is that? Can anybody tell us? Just look at this definition, Joule-Thomson coefficient here, and tell me why the ideal gas, Joule-Thomson, has to be zero. Well, I know it's hard, but yesterday we saw, clearly I hope, that the energy of an ideal gas is a function only of its temperature, and the enthalpy, which is the energy plus the PV product, is a function only of its temperature for an ideal gas. So the Joule-Thomson coefficient is a partial derivative at constant enthalpy, and therefore it's zero for something that doesn't change temperature. If temperatures, if the enthalpy sticks, temperature can't change, so there's no heating or cooling of an ideal gas. Just mind that diagram shows secondary plug or throttle can be anything that restricts flow. It can just be an open tube for that. Because this works, you have an insulated open tube like a pipeline, which there's a pipeline sometimes, the gases and fluids going down there. If it's insulated, then that's a Joule-Thomson expansion. The pressure is always lower downstream than it is upstream. That's the fluid's not going. If you measure the temperatures, A and B, and pressure drops, you measure the Joule-Thomson coefficient for whatever that is. So I just reiterate here that any fluid, pure gas, pure liquid, or any mixed fluid, gas, liquid mixture, whatever, anything that's fluid can be pushed through a restrictor like that with Joule-Thomson coefficient measure. Some examples are given in the math review for thermodynamics and on the next page, which I will put up here. Okay, so I just remind us that the Joule-Thomson coefficient can be positive, and if it is positive, that means the expansion, the pressure is always going down. So if Joule-Thomson coefficient is positive, that means that the temperature is going down. So if Joule-Thomson coefficient is positive, there will be cooling on the expansion. If it's negative, there will be warming on the expansion. And here are some graphs for a few gases, liquids. I'll just pick them up. I've highlighted the axis for Joule-Thomson coefficient is classroom, in this classroom, two tanks, high pressure tanks, pressed gases. One of them was helium, and the other was carbon. Helium oxide. We have tanks like that sitting on the loading dock. We go to next door. We use them in our course all the time. Both of those gases for various things. So I just got myself up here on a hand truck and a thermometer. Actually, it's a digital thermometer. You can stick it in. You've all seen these tanks, like welded across the line. Got a big valve on top and a threaded connection for fittings and for sort of specific threaded different gases. But that's not important. The important thing is at high pressure gas, about 2,000 ounces per inch each one of them. I put a thermometer in that, opened the valve, just cracked it, and let the stuff come out. That's a throttle flow. It happened fast, so there wasn't any much heat flow going across that valve. So it was essentially the Joule process expansion. And when I put the argon on there and opened it, that kept everything down. And I put so when I put the helium on it, it opened it. And so I posed this question in my class. Here are two ideal gases, same family of variant chart. Both just monatomic, little wussy atoms that don't do much. Not much chemistry associated with them. They should always behave similarly. How can you expand one and it gets warmer, you expand the other at from the same conditions in this group? Well, by that time, I had tried to explain to them everything you need to know to answer that question. So I found out to you people, and maybe it's something to think about. But it all goes back to what we talked about kinetic theory, and, interactions, and electric forces. And you can just imagine that as you squeeze these molecules closer together in those tanks, then they interact with each other more often. The electric forces become more important. If the temperature is relatively high, then they bang each other hard, and the repulsions become more important. And we talked about this the other day, they hate each other's guts, and they can't stand together. You open that valve, they not only go out to the atmosphere, which is low pressure, but they go with vengeance because they are repelling one another, and their kinetic energy goes up. And since there's no other energy available, their finish has to go down. And that means that sure. And the kinetic potential energy goes down because they're crowded together. We're up high on the physical wall. As they fly apart, you're going down to a zero. And it's this increase in kinetic energy makes temperature go up. If, on the other hand, they're pretty cozy, they like one another, the temperature's not so high that they're colliding too vigorously, so when you crowd them together, they got some ice. And so when they expand, sure they'll expand because it's a big pressure difference, but they are sort of not too anxious to expand. They pull away from one another sort of lovingly and slow down the temperatures. Here's a graph. So it'll work there, but that's not either, other than it's one that shows pure liquid. And chromatography, they often, in supercritical fluid chromatography, they often, instead of using just pure CO2 as a mold phase, they lace it with some polar solid like that in various amounts to modify the polarity, which has to do with streaking different things through the column. So they don't get stuck there. But nonetheless, just some studies on comparing the mixture of methanol and carbon dioxide in a column, 600 bar inlet, 100 bar outlet. It's a big pressure difference. And look what happens. Pure mud valve temperature just goes flying. Well, liquids nearly always only warm on expansion because they're already crowded together. So when you compress them, they get more crowded. They won't expand very much. They can expand only until the pressure reaches vapor pressure. But any expansion they make will drive the temperature up. But if you take pure carbon dioxide, it starts out because of the temperature here was what we started somewhere 50 degrees Celsius. It started out rising a little bit, and then mainly it just cools off. Cools off big time, 15 degree drop. The temperature time comes out. And look at this one right here, it's about 20%. If I'd done 19%, it would have started at 50 and come out at 50. You think there was no temperature change. Listen, there's your taste buds. All right. Now, if you read through that review, you found on the last page a little challenge. It's related to this one that I will just share with you now. If we consider ammonia gas at 150 bar, 150 degrees Celsius, and here are the properties measuring those conditions. We have the coefficient of thermal expansion, we have the isothermal compressibility, we have the molar volume, we have the Joule-Thomson coefficient, we have the molar heat capacity at constant pressure. And those are all things you can put in this equation to calculate the change in the difference in heat capacities. So I'll ask you to do that. If you do, you ought to get this result, I hope, 4.218 bar. Also, then calculate the heat capacity constant volume, which should be about 6.71 bar. And to calculate the ratio of heat capacity should be about 7.3. That's the kind of thing students better understand to be able to do. I'll stick this in, print that out, scan that, and put that on the web this afternoon. All right, so put that to rest while we do the following. I tried to write this out a little bit. We are going to take a brief look at the heat capacity gases. Try to understand some of this concept more. So when a gas gains energy by heat flow to it, that energy is partitioned amongst all various repositories for energy in molecules. Now, what kind of repositories might that be? Well, molecules are moving around in a box or container. We call that translation motion. And if they're not monatomic, they're also tumbling around. We call that rotational motion. And they probably are also vibrating. Bombs are vibrating. They're pinning machines. So we have translation, rotation, vibration, places for energy can be accommodated in molecules. So we put energy into a gas, and where does it wind up? It winds up in all these places. These include translational energies, which we know about. Rotational energy, I just write as 1/2 moment of inertia times the angular speed squared. Vibrational energy, yes, we remember, has two parts. There's always trade-off of kinetic for potential, kinetic for potential. That's what vibration is all about. So you can't have vibration without having both kinetic and potential. So there are two cubby holes in translational movement. There's one each in translation, and in vibration mode, one each in translation and rotation. Now, classical mechanics includes embraces the equal partition theory which we studied earlier. Now we're going to come back and revisit it in this video. And the equal partition theory, says that equilibrium, the thermal equilibrium, all repositories for energy storage in an electric system share the available energy in equal proportions, partition equally amongst the various places where we can simplify it. And we found that worked pretty neatly back when we were looking at things like the interpretation or explanation of the Coulomb heat rule for heat classes of metals, treated atoms and metals, treated dimensional oscillators, did a little heat partition on that. The energy, the average energy of gas molecules was 3 half kT, 1 half kT per translational mode. And we said, well, these vibrators would have 1 half kT per vibrational mode of kinetic energy, 1 half kT per vibrational mode of potential energy, or kT per mode, 3 modes, 3 kT. That was the partition theory. This is revisiting that same idea. Well, let's talk about how many degrees of freedom there are in molecules. Now we're not talking about metals, metal crystals. Degree of freedom of molecules is 3 times the number of atoms of molecules. Everybody understand that? Agree with that? That principle in mechanics and physics. Where n's the number of atoms in the molecule. So here's a little table. We're going to look at different kinds of atoms, count up all the degrees of freedom in the molecule, different kinds of molecules. If the molecule has just 1 atom in it, it has only 3 degrees of freedom, and they are all translational. There's no real, I got mine. Show and tell here. There it is. You say, well, it can be rotated, yes, but that rotational part is all taken out in the treatment of the electron motion. Not part of the conversation here for the physical properties of gases. So that's very simple. So the next one is the diatomic. Diatomic, we have 6 degrees of freedom. We'll always have 3 of translation. And we have what? We have how many rotations? Well, we have 2 degrees of rotation, that way or that way. So if you take this atom here and put it anywhere on the surface, it's just associated. That's what if you imagine this atom's anywhere on the surface of a sphere, it can reach any place on the surface of the sphere by that rotation and this rotation, or a combination of just 2 degrees. That rotation along that axis doesn't count because that's the same as the electronic motions in this atom. Well, 3 and 2 are 5, so that leaves 1 over. That's the vibration, and of course, there it is. So we can see that. Now we have polyatomic with n greater than 2. 2 cases. Just imagine this is a carbon dioxide molecule. So it's linear. And it just has 2 rotations, the same as hydrogen, chlorine gas. So we have 3 translations, 2 rotations, and how many vibrations? 3n minus 5. All right. Now we have the possibility of having a nonlinear molecule, and most of them are nonlinear if they have more than degrees of translational freedom? 3. How many degrees of rotational freedom? 3. That one, that, and that. And how many are left over for vibration? 3 and minus 6. Right. For each molecule, the energy of the molecule is the sum of its translational energy, translational mode, rotational mode, vibrational mode, the sum of each of those. And so that's equal to translation, 1/2 mdx squared, so that mdy squared, so that mdz squared, and those are the translations, 3 modes. Right, rotation, we have 1/2 I omega squared for each rotational mode. 2 for 3. 0, 2, or 3. For vibrations, we have 1/2 mdx squared, that's the kinetic energy of vibration, and 1/2 kx squared. This is not Boltzmann's constant, but rather Hooke's law constant, the elasticity of the bond. So this is kinetic energy, and this is potential energy. This is Hooke's law constant. So, classical efficient theorem requires the energy stored in these repositories on average be 1/2 kT for each quadratic term. So the average translational energy per mode is 1/2 kT. The average rotational energy per mode is 1/2 kT. The average vibrational energy per mode is 2/2 kT, 1 kT. All right, makes sense. So combining those and writing on a molecular or molar basis, and looking at some state properties of an ideal gas molecules in equilibrium at temperature T. And we're going to talk about different kinds of molecules, different numbers of atoms. We look at the translational molar energy, translational rotational molar, the molar rotational energy, the molar vibrational energy, the total molar energy, the heat capacity at constant volume, the heat capacity at constant pressure, which is just R plus Cv, because it's an ideal gas. Oh, if n equal 1, we're back here to our single little one atom molecule. The molar energy is 3/2 RT. There is no rotational nor a vibrational energy. So the total energy is 3/2 RT. We have ingrained in our memory now that heat capacity at constant volume is partial of energy with respect to temperature at constant volume. This is the energy, so differentiate with respect to temperature, you get 3/2 RT. That's not just for the ideal gas, that differentiation. Heat capacity at constant volume is partial of E with respect to temperature at constant volume. Heat capacity at constant pressure, we just have to add R to it because it's an ideal gas. 3/2 R plus 2/2 R is 5/2 R. Diatomic molecules. This will still be 3/2 RT for the translational molar energy. Now we have 2 rotational modes at 1/2 RT per mode on a molar basis. And so 2 others adds up to RT. We have 1 vibrational mode at 2/2 RT per mole, adds up to RT. So we got 3 and 2, that's 7/2 RT for the total energy, 7/2 R for the heat capacity constant volume, and 9/2 R for the heat capacity constant pressure. of these multi-atom molecules, more than 2 atoms, we have to treat these 2 situations separately. If the molecule is linear, like carbon dioxide, then we have the 3 halves RT for translation. We have the RT, two rotation modes. So we have 3n minus 5 RT for the vibrations. And add these all together, you get 3n minus 5 halves RT for the total. You differentiate this with respect to temperature, and for the decapacitor constant volume, it's 3n minus 5 halves R. And for the decapacitor constant pressure, you add R, so it's 3n minus 3 halves. Look. And the last one, nonlinear molecules. 3 halves RT for the translation, 3 halves RT for the rotation, because there are 3 modes of rotation. 3n minus 6 RT for the vibrations. So add these all together, and pretty clearly is 3n minus 3 RT. Differentiate it for decapacitor constant volume, 3n minus 3R. Add R, 3n minus 2R, so then we got the table complete. So those are the things we could easily do just based on classical condition here. That's what that classical theory predicts for these molecules when they're not packed together, so there's a lot of other stuff that we're in. All right, so I like partition. I like to think about this partition in this way. I like to think about an example, a dipont molecule. And I've drawn little buckets or tubes represent the places where you pour the energy, fill them up. And so we have 3 of those for translational mode, X, Y, and Z. We have 2 for the rotational mode. There's 1 rotational mode, 2 rotational modes. And we have 2 for the vibrational energy, 1 kinetic, 1 potential. So here are the buckets. Here's an energy scale, and here is 1/2 kT on that scale. So we pour the energy into it, and it runs out and sinks a level right through there. That's what. So it predicts for this dipont molecule that the energy molecule is 3 halves plus 2 halves plus 2 halves kT, 7 halves kT. Same thing we have in that term over there. Now we're focusing down on this one little tiny molecule. The lower energy is Avogadro's number times the average molecular energy. So it's just 7 halves RT. Because Avogadro's number times K is R. So the theory says that for a dipont molecule, just to review that one line for the chart we had a moment ago, is that the heat capacity constant volume over heat capacity is 7 halves R, and over heat capacity constant pressure is 9 halves R, and the ratio of heat capacities is 9 halves, which is about 1.285 or something. Yeah.
Isn't that CP over CV? So shouldn't it be 9 over 7?
Well, 9/2.
Yep.
I had a 7 there. I don't know why. Thank you. All right, so that's the theory. Now, remember about science. We're studying science. We're concerned with observations, lots of behavior matter, about trying to find rules that behavior follow and trying to interpret what is there about matter that causes this behavior. So there's some back up. All right, we will compare the efficient theory or prediction with the observed behavior for nitrogen. That could be anything, this is a good choice. And then gases at low enough pressures that we're not having to worry about having to account for irregular forces. So that's practically pressure for nitrogen. And you gotta really squeeze through all that before they get to the point. And we're gonna look at some properties and compare the heat efficient theorem with the experimental result for nitrogen gas. And the molar energy theory says it should be 7/2 RT or 3.5 RT. That well, the heat capacity constant volume then is the derivative of the energy, so theory says it should be 7/2 R, 3.5 R, it's 2.503 R, which is about 5 hours away. And the ratio of heat capacity, so theory says should be, thank you,
9/7.
I got it.
Okay.
Right there. 907, 1.286 or thereabouts. And the external value is 1.4012, which is about 7 hours. So it looks like the energy of nitrogen molecules are about 2/2 RT or KT short on the average. 2/2 KT per molecule on average, or 2/2 RT per mole. Just RT. So the question is, what is there about matter that causes the observed behavior, or you state what's wrong here? All right. Now, this is a portion limited topics of physical chemistry, and not included in that list of topics for our curriculum. It is the one that is absolutely required to answer that question. But because two things. One, let's say, study of this part of the matter is so incredibly dull that it needs using up an awesome. And two, don't really need to know this stuff. I'm sure you already know it, but here again, that the reaffirmation, I think, might not be inappropriate. So we're going to digress a little, and I'll answer that question. Now this won't be a full-blown hot shot answer, will be just a quick, give you something a little flavor. So, what's wrong? There's a problem here. So, the nature of this problem, which is a pernicious problem that pervades all of our science, if you look at it closely enough, derives from a fundamental weakness in the human condition. In my opinion, I'm just telling you now, I'm not taking this out of text, I'm just telling you, all right, that we, human beings, scientists, we think we're more than nature has endowed us to be. And we feel we should be able to see the universe, see the world as it actually is. But we cannot do that. At least not in the finest state. We cannot do that. So For example, suppose that we wish to locate a particle. Locate this thing. How do we go about doing that? It's dark in here. We had to go around. We had to interact with the object. How to do it? It was lying here. What do we say? It's a light. Bounce it off it. Bounce back to our eyes. In general, if you're trying to locate a particle, you have to send a messenger that is responsive to its presence and can report back to us that it had an encounter that suggests there was an object there. That's who we are, and that's the information. There's no way that we can locate that particle without interacting with it and without interacting with it in an energetic way, and perhaps even disturbing, changing. So the truth is that observations always perturb the particle in some indeterminate way and leaves it different than when we found it. Now, some years ago, you were probably none of you were born yet. But some years ago, we said some fine young men often to rendezvous with the moon. I remember that much. Very exciting. They had to travel good distance through space, not just the 220,000 miles to the moon, but they had to go on a big path. They were pretty confident when they got there and they looked out the window that there was some moon. And that's a particle, and we observe it, but we don't knock it out and circle it up. We can't land a spaceship on it. But why is it particle is more common in study of chemistry? Why is it something like an electron? Okay. We try to find an electron. Then what do we have to do? We can't see it with ordinary light. We have to interact with it somehow. And any observation we make on that electron, we did right here, this phase came from, and we did something that came back and said, oh, there's something right there. We say, oh yeah, but you can't be sure they still have to find it there again. So you go back and look. It's not there. It's a thing. So, for this reason, we need to give fair consideration to two questions, which I will now ask. And I'm sure you know the answers. Can a particle, any particle, or any electron, or some electron, or anything, can a particle be at rest? Okay, I see one head shaking. No. Anybody agree with that? No. You say no? No. Anybody else? Everybody agree? We take a vote. No. That's the party line. And I say to you, in all sincerity, hell yes, why not? Who the hell are we to tell a particle that it can't be at rest? That is the arrogance of the human being, playing God, which I told you we do when we create theories. On our theory, we can say our molecule has to be moving or whatever. But we're talking about real matter now. We're not talking about the deep. That's the arrogant nature of who we are. Teach people like you, people all over the world, that a particle cannot be at rest. And I'll say BS. Prove it. There's no reason to have us do it. No reason at all, other than just to preserve our dignity. say, yes, the particle can be addressed. As far as I know no reason why it can't be. Then, next question. Can we observe a particle to be addressed? And what's the answer to that?
We haven't thus far.
Pardon?
Said we haven't thus far.
I'd say can we, based on who we are. And the answer is no. We cannot observe particles to be addressed. Why? Because we're human beings, we're not gods. We're human beings. And the only way we can locate a particle is by interacting with it. And if we interact with it once and disturb it in some way that we've not got certain details of it, and go there and interact with it a second time, different time, and say, oh, it was here then, it's here now, time difference, we know it's going this direction, this speed. You say, oh, yeah, well, then we predict what's going to be out there, and go out there at that time, but it's not there. Why? Because each observation knocks it off course. Each observation changes it to something determined. We can't know. Could it be at rest? Oh, hell yes. Could we find it there? If we found it once, and wanted to prove it's at rest, we got to go find it there again. And if it's not there, we say it wasn't at rest. How do you know what it was? Well, what I would like you to think about, try to understand, is that because of who we are and the limitations on our ability to determine the behavior of matter, especially small pieces of matter, like electrons and atoms. Because of who we are and the uncertainty in where these particles are and how they are moving, the uncertainty to us, not to them, not to a God, but to us, or any creature with our limited powers of observation, to discern. We must build into our models that action. Failing to do that leads to trouble, leads to destruction, and lots and lots of others. So we need to build into our models the very basis of our limitations, the uncertainty of where things are and how they are moving. Now, does that make sense? That seems a reasonable thing. Is there a way to do that in an open and honest and defensible manner? And the answer is absolutely yes. An honorable, open, honest, defensible manner. Why then is it never ever done that way? I don't know, but I suspect that it's just the arrogance of our species that in order to preserve what we think is our rightful dignity,